All right, hello everyone, and thanks for attending today's CGD seminar. Before we get started, I'll remind you of our CGD Code of Conduct here, where we offer constructive feedback, share the air and make sure that all voices are heard, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. I'll ask that everyone please keep themselves muted during the seminar and hold any questions until the end. Now it is my pleasure to introduce today's speaker. Magdalena Balmaseda is a principal scientist and head of the Earth System Predictability section at the European Center for Medium-Range Weather Forecasts. She received her PhD in physics at the University of Alcalá de Henares in Madrid, Spain, and after a postdoc at Oxford University, joined ECMWF in 1995. Her interests and expertise include forecast system design, the predictability of weather and climate, probabilistic forecasting, and scale interactions in the climate system. She led the Ocean Reanalysis Intercomparison Project and is a leader in advocating for coupled data assimilation and in bridging disciplines between weather and climate, observations and models, and ocean and atmosphere. Her talk title today is Initialization and Forecast Strategies for Seamless Prediction. So Magdalena, feel free to go ahead and share your screen and take it away.
Hello, good morning, everybody. And thank you, Dan and Judith, for inviting me to give the seminar here in this seminar series. I will try to share the screen. Bear with me a moment, because sometimes it's slow. And I will also stop my camera now. So it takes a few minutes until it gets into full presentation mode. Hopefully it will do soon. In the meantime, I just take the opportunity to say that this is the contents of this seminar are part of a training course that we give, the training course on predictability at ECMWF. So as such, it will not contain any new material. It's more consolidation of existing knowledge to the service, to the application on operational forecasts. And I try again, see whether it works now. Bear with me. Yes, it should be the full screen now. Is correct?
Yes, it looks good.
Yeah. Okay, so I will set up, in this seminar, I will set up the scene, initialization into context, and talk a little bit about initialization shock, forecast drift, and calibration. I will provide some examples on the initialization of the ocean, because this is the, apart from the atmosphere, is the most mature component for initialization, and it's also my expertise. And I will try to compare what we do at ECMWF with other initialization strategies. Finally, I will touch quite briefly on ensemble generation to sample uncertainty on ocean initial conditions and forecast strategies for dealing with model error. So, I mean, this is, we are talking about seamless predictions. So they are forecasts beyond the weather time scales. And as we know, the basis for these forecasts is that in a system with multiple time scales, there are two sets of predictabilities, two paradigms. From the point of view of the atmosphere, this sort of predictability is a predictability of the second kind, in which the boundary conditions will change the probability of occurrence on the of the atmospheric circulation and occurrence of regimes on large scale precipitation. But from the slow component perspective, this S2S or seasonal to decadal, this prediction problem is an initial value problem. So it's a predictability of the first kind, and we need to initialize this slow component. So which are these slow components? They are Prognostically, they are the ocean. I think most of the systems, Earth system models have ocean, soil moisture, snow, sea ice. Stratosphere is also slow compared to the troposphere. There are also boundary conditions that are not prognostic, like CO2, solar activity, aerosols, land cover or land use, or land and lake masks, for instance. And little by little, these components are being included, put into prognostic mode in full Earth system models. There are ongoing efforts on including prognostic stratospheric ozone and vegetation. So the initialization as such is an essential component of the forecasting system. In fact, the initialization is what distinguishes a forecast from a projection or a simulation. So in a forecast, we have three distinct phases. We have the initialization, which is the process in which we translate the observational information from the real world into the model world. So this is usually done with data simulation, that is basically Bayesian statistical techniques. Then once we have the information into the model world, propagate it into the future via a forecast model that usually we say dynamical models, but they could be empirical as well. And finally, we also need to complete the cycle by projecting the output from the numerical model in the model world into the real world. And this is the calibration, that often also called forecast assimilation, because it uses the same Bayesian techniques as the data simulation. So in this talk, we are going to talk about this initialization. And I would like to say that the way we initialize the model also depends on which forecast strategy we want to follow. So that should become evident at the end of the talk. And the problem of the initialization, or the questions for initialization, is that this is an approximation, because it's never going to be perfect. It is not perfect because the model is not perfect. So it's also because the observations may be insufficient or they have errors. And also because the data simulation itself, the translator between these two worlds, may have deficiencies. And I would like to show this cartoon to illustrate the problem. So imagine that we have a forecast lead time. I guess you can see my cursor here. And we have a phase space where we have the real world, more or less here in this blue line, and the model climate or the model world in a different one. And then we initialize close to the real world. That's what we do at TCMWF. And as we initialize the model, we need to put the model attractor close to the real world with the assimilation increments. But as we start the forecast, these initial conditions, this state, not only propagates the information into the future, but it also drifts little by little into its own model attractor. This is a good case because during this phase, we have more skill. If we see the difference between the trajectory and the real world, we have skill. We haven't reached the climate yet. But sometimes this initialization may not be perfect. And instead of being a monotonic increase, we have some initial adjustment that cause what is called initialization shock. In some cases, that could be quite pathological cases, this initialization shock can overshoot and even go beyond the error of the model climate. But in general, initialization shock is quite fast error growth at the beginning. And something to consider as well is that we have a system with multiple time scales, and it's a nonlinear system. And it could be that these errors may interact with the mean state and create problems. So I guess one example that I tend to use is the sea ice. If we manage to melt all the sea ice during the initialization shock, we enter into a different equilibrium, and then it's very difficult to restore the model to its own, to something close to the real world. So sometimes if the nonlinear interactions are such that we overshoot them, then this could result in degradation of scale. For that, some people have considered what happens if we try to put some empirical corrections or flux adjustment to make sure that the model doesn't drift too far away and never reaches the threshold of the nonlinear interaction. And I will come back to this idea later on. So this process of drift or the model going towards its own attractor results on systematic errors. Systematic errors usually we are quite simple-minded and we think systematical errors in the first moment of the distribution or in the mean state, and it's called bias. And this is something that it depends on the model version, the physics, the resolution, but it also depends on the initialization. So a same model with different initialization procedures can lead to different biases and also different drifts. Drift is just the time dependence of the bias, and that's the only thing. We also have errors in the second moment of the distribution, and it's as exemplified here on the right-hand side, where we see the ratio of variance between the forecast and the observations. And in this case, this graphic shows two different initializations. The impact of two different initializations is the same model, but with different drifts, and therefore they will have also different estimation of the interannual variability. And this is a sign of nonlinearity somehow, no? Because it's the same model. This is not the property of the model, it's the property of the initialization. So that's something important. The systematic error depends on the initialization as well, at least in this forecast. Maybe we'd reach a lead time in which that dependence stabilizes, but in seasonal time scales, definitely depends on the lead time. So, okay, what is the initialization problem? Is the production of optimal initial conditions. And in the case of the atmosphere, this optimality is relatively well defined. And we have a metric, and the metric is the forecast error in the first, say, 6 hours of 12 hours of the forecast. And this can be controlled with the variational 40 bar, for instance. But this is not the case for persistent components. We don't have this methodology for the seasonal forecast or for the decadal forecast. So we are not going to go with optimal initialization. We are going to try to be a little bit more practical and say initial conditions should represent accurately the state of the real world. And they should also project into the model attractor so the model can evolve them. And this is difficult in the presence of model error and initialization shock and forecast drift, but that's what we are trying to do. So we know that also that there are practical requirements arising from calibration, that we need forecast errors that are stationary. And we also need consistency between the reforecast and the real time. So I'm going to talk now about this reforecast in case you don't know. So the forecasts are an integral part of the forecasting system, especially when a model has errors. So imagine that we have a forecast today. We launch a set of ensembles to estimate the PDF of the future occurrence. But this is in error, so we need to calibrate and to refer it to something. To estimate, what we do is try to estimate the model climatology, PDF of the model climatology, by issuing a set of retrospective forecast. That's why they are called Reforecast, over a given past period. And then we estimate this PDF. But it is important that this model PDF is consistent with the real-time PDF. So the comparison makes sense. And that imposes conditions on the quality of the initial conditions for the reforecast that they usually are given by reanalysis. So to initialize Earth system models, S2S, S2D, we need some sort of reanalysis, Earth system reanalysis as well. So the reforecast, they are not only used for initialization, but they are also used, well, apart from the calibration of the forecast, they are used for detection of the extreme events, also in the medium range. For skill assessment, it's important to know the quality of the forecast before you issue the forecasts. They are very useful, especially now that we have this reforecast in public databases like S2S or C3A or seasonal databases for skill assessment, for predictability and evaluation studies. They are also essential to guide system design because they allow identifying critical errors limiting forecast scale. And then the reanalysis, finally, they are used for climate monitoring, which is very important. So what are the requirements for the reanalysis? As I said, is consistency between the reanalysis and the real time. So calibration makes sense. Temporal consistency through the record and faithful representation of a wide range of time scales from diurnal cycle to seasonal and trends variability. So seasonal variability and trends. And this is quite challenging in the presence of model error and a changing observing system, as we will see. The initialization in the reanalysis has to be accurate and physically balanced. So there is a balance estimate of the real world and associated uncertainty. So observational information can be propagated into the forecast and relevant processes can be quantified. And this reanalysis should go back as far as possible. There is no limit. There is only practical limits. So those are the general concepts. And now I'm going to pass to talk more specifically about the initialization of the ocean. So the ocean is interesting because it's not only a slow component, it's a dynamical slow component. So it's not only a question of initializing the thermodynamical memory, say the ocean mix layer, but also the ocean dynamics. And because there are waves that propagate and they can lead to forecast scale. And this is the typical example of ENSO, where we see here Hoff-Muller across the equator of the thermocline and sea surface temperature on the right. And we can see these sort of Kelvin waves that propagate eastwards, and they precede the appearance of the anomalies at the surface. So this is the basis, this propagation is probably the basis for the seasonal forecast, and we need to capture that correctly. So how do we initialize? The simple way is to have an ocean model. Well, the simple essential ingredients is an ocean model, atmospheric fluxes or atmospheric forcing, usually from atmospheric reanalysis. But we also have observations. So we try to constrain the evolution of the ocean with these observations via data simulation methods. These observations are sea surface temperature, in situ temperature of in situ observations of temperature and salinity from moorings, Argo, SDTs, and also we have satellite altimeter, and that's what we do. The atmosphere is that the data simulation in the ocean goes beyond constraining just the chaotic variability. the data assimilation will try to reduce uncertainty and errors in the surface fluxes, because the ocean is quite a forced system. And it will correct for ocean model errors. So this is because we have huge uncertainty and errors in the surface fluxes. We need additional information. So here I show two diagrams. This is a bit old slide, but showing how the uncertainty in the wind stress in the equatorial Pacific from two different reanalysis products translate in uncertainty in the ocean heat content in the equatorial Atlantic. This uncertainty is quite large in an ocean-only model. So with data assimilation, can we constrain this uncertainty? And yes, we can constrain the uncertainty to a large extent, but this is not enough. We should try to improve also the ocean estimate, and I will show that it's possible, not easy, but it's possible. And we should also try to improve the skill of the forecasts. So what about what do the observations do to the mean state of the ocean, or to the ocean in general, to the ocean reanalysis? Here is also an old diagram that shows the mean assimilation increment, temperature assimilation increment across the equator as a function of depth and longitude, average over many years. And what we see here is that the assimilation of temperature, in this case of profiles, is trying, in the diagram, if we had this is the mean state of the ocean-only simulation. The data simulation is trying to do two things. It's trying to lift the thermocline, the tilt of the thermocline, and it's trying to deepen the ocean heat content across the equator. So, and that's a very clear signal. But we don't have observations for all the records. The observing system, especially the ocean, is changing continuously. And this shows just the data coverage in June 1992. It was a year, meteorological year, I think, and there were many observational campaigns. In 2005, for instance, we have a very different observation coverage. And here, this other graphic shows the time evolution. And we can see the advent of Argo, how the number of observations have increased so dramatically. So this will have impact for the estimation of the ocean variability during the reanalysis. And in fact, it did. And I'm going to show some pathological case. One always learns from problems. And this is from the first reanalysis that we had in the year 2000 or 2002. We had, I mean, the black curve is an ocean-only simulation. And when the Pirata array, observations from Pirata array were available in the equatorial Pacific, we started assimilating them. And what happened here, this is the depth of the thermocline, is that the thermocline was very diffused in the forward model. And the observation said, no, I want to be shallower. And it creates a huge jump. This is a spurious climate variability. So, and this will lead to errors in the seasonal forecasts if we were to initialize an ocean with this reanalysis. So the way we try to alleviate it is by applying some bias correction. So I don't want to go too much into details, but the idea is to have, as part of the assimilation system, one estimation of the mean model error with an autoregressive model and taking the assimilation increments. Here is accumulating them with a certain time scale. And then we apply them during the assimilation process. We apply these biases as corrections to the tendencies, to the model tendencies. And this is a way of extrapolating the observational information, if you want, into the past, because we have a first guess of our error by doing the mean of the assimilation increments. And you can see it here in this diagram. And if we apply this from the beginning and we apply this bias correction, we get that the observations can have an impact far back and reduce or alleviate the problem of this spurious interannual variability. So this is something that we have started doing in the ocean. In the atmosphere, traditionally, the first guess or the model is considered that is unbiased. But lately, there are developments that they are applying this bias correction, estimating and applying this bias correction also for the stratosphere. And we are considering applying this bias correction for the next generation of ECMWF atmospheric reanalysis, ERA6. Work is in progress. So after that, we have seen that we have corrected the mean state, but what about the interannual variability? This is not easy to evaluate, but luckily, altimeter provides a good continuous record of interannual variability. So if we do the correlation of the sea level from the ocean reanalysis and the sea level from the altimeter, we can see how the interannual variability improves. And here I show 3 graphics. One that is the correlation with the altimeter of an ocean model, forced only with surface fluxes, no ocean data simulation. This one shows when we assimilate in situ observation. And this one is when we assimilate also altimeter. Obviously, when we assimilate altimeter, the correlation increases. But then we have to ask the additional question, the complementary question. Does the assimilation of altimeter improve the fit to the subsurface observation? Because it's very easy to improve the correlation with altimeter if you assimilate altimeter. But the proof of the cake is, say, does the assimilation constrain and correct the vertical profiles? And this is more difficult. But we manage very modestly, but we manage. So here is the RMS error of the ocean reanalysis with respect to the in situ observations. For this integration, no ocean data simulation, with data simulation, and with altimeter assimilation. So every little helps. And finally, what we want to see is whether the data simulation improves the forecast scale. And indeed, it does, especially for ENSO. That's where we dedicate most of our efforts. We can see that assimilating observations in our latest seasonal forecasting system, shows here, is equivalent more or less to 15 years of model development. So here what I'm showing is the forecast lead month with correlations about 0.9 in Niño 3.4. So assimilation of ocean observation help brings a skill. What we don't know, and this is something, if any of you are working on this subject, is why. Is it because it's better representation of the interannual variability, or is it because we improve the mean state and therefore the interactions with the variability during the forecast phase? So we don't know whether it's the improvement of the interannual variability in the initial conditions or in the forecast. So much for the ECMWF initialization. So what about other strategies? So far we have seen that we need a consistency with the real-time forecast and temporal consistency. No? We have seen this. And we also have seen that this can be difficult because there could be initialization shock. There could be changing in observing systems that makes errors in forecast non-stationary. And it could be flow-dependent error. And I'm going to show a little bit of this because this slide is a paper by Kumar et al. I think exemplifies these cases, these problems. So what we see is very clear non-stationary errors. It shows the errors in SST and seasonal forecast at 1 month lead time and an 8 month lead times. We see that there is a clear seasonal cycle of the errors. This is scattered forth in the way we have the forecast strategy, because we do reforecast for each calendar month. But there are also unknown dependencies. There are non-stationarities with some interannual or decadal variability. This is due to changes in the observing system, and or probably that the model doesn't respond well to trends. So, and you can see that these errors are non-stationary. And you can see that the drift or that there is a sort of initialization shock, because in some cases, the error at the 1 month lead time can be larger than the error at the 8 months lead time. So this is an example of a pathological cases on initialization. And those are dangerous because these temporal inconsistencies and non-linearities can render a posteriori calibration invalid. So let's talk, we have talked about drift before. What about initialization shock? So the initialization shock implies that the data assimilation process has created imbalances in the initial conditions that are not supported by the model physics. And the observational information is rapidly lost via adjustment processes that deteriorate the skill. So what causes initialization shock? It could be deficient data assimilation, like insufficient physical constraints, or data assimilation forces scales that the model doesn't have, is not able to represent, or too much weight to the observations, or poor, that in the case, poor quality control of the observations, we are putting observations that are not good. But there are also other reason, and is that the initial conditions had been produced by two different models, by two different model systems. This could happen if we have separate initialization of the ocean and atmosphere, or if we have different model cycles. And this is particularly important for the land, putting initial conditions for the ocean, from the land and ocean, from one model into other model is quite complicated, and it can lead to initialization shock. But we also see it on the atmosphere. And here, this is an example where we were trying to evaluate the values of coupled initialization. And we had an uncoupled initialization, the two systems exactly the same, but in an uncoupled mode. And you see in how the RMS error, I think it was, well, 1000 hectopascals. Yeah, when we do coupled data assimilation, we have a slower error growth. But when we got very difficult, very bad error growth is when we had reanalysis. We tried to initialize from reanalysis that they were produced with a model cycle, atmospheric model cycle, very different from the model cycle used in forecast. And there, perhaps the convection was not in balance, or the radiation, and there were very fast errors developing. This is at the weather time scales. I mean, this is 10 days. And so we see errors in the first day developing very quickly. Usually we don't pay much attention to this problem, but we should. That's the message that I wanted to send here. So much for initialization shock. Now let's go to this idea of the real world and the model world. At TCMWF and in many forecasting systems, we follow this approach of the real world initialization, or it's called full initialization. Being close to the model, to the real world, is perceived advantageous, and the model may slowly drift to its own mean state, but in the process, we are close to the real world, and this brings a skill. When decadal forecasting started, there was this idea of anomaly initialization that started decadal or longer, trying to avoid forecast drift, but by initializing the model around its own attractor. But what happens with the seamless forecasting system, this paradigm, this bifurcation give us trouble. So at first sight, this will not allow for a seamless forecasting system. But I would also like to reflect that anomaly initialization is not the same that initializing in the model attractor. And even if there are caveats for the full initialization, there may be also problems with the anomaly initialization. And I try to summarize here. This is, I think this has been discussed in several papers. But in the full initialization that and this forecast strategy that we have seen before with the Reforecast is the same as in the medium range. We apply it for seasonal as well. The only difference is the slow component, in this case, the ocean model. The bias is taken into account into the, during the data assimilation processes. A posteriori calibration of the forecast is needed, and this calibration depends on lead time and depends on the season. And therefore, this Reforecast strategy is quite expensive. It has something to consider is that if we had a couple data simulation, the bias correction estimated during the initialization could be applied during the forecast process. And in that case, it may reduce drift, initialization shock, and improve forecast scale. In contrast, the anomaly initialization, I exemplified this with this diagram where we have a long couple integration. And then we try to put the observed anomaly into the model and to launch a forecast. So you only need, you don't need recalibration. In principle, you don't need a reforecast. You only need one, the long integration and the initialization for this forecast. So it's much cheaper in principle. So, and that was also one of, this is one of the advantages. But it is seen that the forecast still needs calibration, and it's not straightforward because we don't have the reforecast. And there is other more fundamental problem, that is, what is the definition of an anomaly? If you have an observation first time, you don't know what an anomaly is. So these, they are also based on reanalysis. So you need to do a reanalysis regardless, and you will have the same problems that we had with the reanalysis for the full initialization. From the mathematical point of view, there is a difference between the full initialization and the anomaly initialization. This anomaly initialization is called bias blind algorithm, in such that the bias or the mean state is removed from the estimate before applying the increment. While in the full initialization with bias correction, the bias is estimated and taken into account. So it is added. So much for the initialization and strategies. And what about the sampling the uncertainty? I'm going to talk again about the ocean initial conditions. So we know that in the medium range, there is quite a lot of work on optimal perturbations for sampling initial uncertainty, these singular vectors. But because for the same reason as we don't have optimal initial conditions, we are not going to have optimal perturbations either. So we opt for something more practical, that is known uncertainties. So which are those known uncertainties? If we have a couple reanalysis, ocean reanalysis or ocean simulation, we know that we have uncertainty in the surface forcing. So that's what we do. So we perturb all the surface fluxes. Now we have the 20th century reanalysis and ERA 5 that provide uncertainty for solar radiation, winds, etc., etc. So we take that into account. We also, in the ocean, it's important to take into account the uncertainty in the spin-up on the initial conditions at the beginning of the record, because the ocean has long memory and it's going to take a long time to converge. And this shows here examples for the 20th century reanalysis that we had, the CMWF. We tried to sample the uncertainty at the beginning in the 1900s, and the assimilation is only able to collapse that uncertainty more or less after the 60s. Before that, there is a huge in the ocean integrated quantities of the ocean heat content. The upper fields is easier, but not if you consider the bottom of the ocean. And we also take into account the representativeness error of the observations. So the observations are punctual, and they represent certain spatial and temporal scales that the model may not capture. And for that, what we do is in the case of satellite or dense profiles, we thin the observations and we thin them randomly. So each ensemble member of the reanalysis, we tend to have an ensemble of reanalysis. Each ensemble member will see different realizations of the observations. So we do it for the altimeter, for the CIs, and also for the dense profiles. So, and we also perturb the positions of the observations. So by a quantity that is, so this commensurable with the grid spacing. Instead, in the atmosphere, they sample, they perturb the value of the observations, but that has the problem of decorrelating the profile and disrupting the stratification, which is quite important. So that's why we keep the profile the same shape, but we perturb the position. So how does it work? These perturbations, by construction, they don't have flow dependency. The only flow dependence that they have is the seasonal cycle, either because they are stratified by calendar month or calendar week. So a way of seeing how they behave, and also whether there is flow dependent, and also to show the benefits of the coupled data simulation, is that the coupled data simulation will give you flow dependent without having to create forcing perturbations. So for instance, we compare this reanalysis of the 20th century uncoupled with these perturbations that I have described, but we also have the counterpart, the coupled reanalysis for the 20th century. And we can look at, for instance, the solar radiation, the standard deviation of the perturbations that we put. So in the uncoupled, we don't have these decadal variations, but in the coupled reanalysis, we do have, and the spread in solar radiation, in this case, decreases as the observed system improves and the solution is better constrained. But it also has an intraseasonal flow dependency. And to illustrate that, I'm going to show some Hofmüllers of the equator, Indian Ocean, Pacific Ocean, Atlantic Ocean, and time. This is 2 years of from 95 to 97. Sea surface temperature, thermocline depth, zonal wind stress, and freshwater flux. And we can see El Nino 97, 98 with the displacement of the warm pool. And the deepening of the thermocline, the propagation, as you can see it here, the deepening of the thermocline. You also can see the big MGO, I think the westerly wind bars that triggers El Nino there. And you can see also the bifurcation in the Walker circulation in terms of precipitation and how the convective cells split into the Indian and the Pacific. The eastward propagation of the convection in the Pacific, and here due to the Indian Ocean dipole, there was a westward propagation. So
Magdalena, you asked for a 5-minute reminder, so here it is.
Yeah, okay, thank you, Dan. With the perturbations that I've shown before in uncoupled mode, it's very difficult to see any time dependency. any flow dependency of these perturbations, maybe a little bit on this tropical, maybe, but very, very tiny. However, when we go to couple data simulation, we can see these strong instability waves that they disappear when there is El Nino. We also see the thermocline, these instability waves project also in the thermocline, and we don't have them here. We also see the uncertainty associated with these westerly wind bursts and with the precipitation. So that's a very good news, I would say. And some final words on the forecast strategy for dealing with model error. So in this diagram, the three phases is of the forecast: initialization, model propagation, and calibration. We have model error in the three of them, but we treat the model error differently. So while in both in the calibration and in the initialization, we may consider bias, during the forecast, we don't consider the bias. And also we put some stochastic physics that are not constrained by observation. So maybe we would like to go towards more, a better and more consistent treatment of model error that will consist on stochastic models and observational constraints. This is a great field for machine learning applications, incidentally. And some thoughts is that in the forecast mode, applying these corrections, they are called flux corrections, is usually has been thrown at. But in ocean reanalysis, we need them. It's essential to apply. They are not flux corrections. They are corrections to the tendencies. So maybe we need a more general framework to think on these corrections. And to me, this is the coupling of coupling dynamical models with empirical stochastic models. This is something that Hasselmann proposed quite a long time ago when he started thinking on Earth system modeling. This coupling was essential. And actually, as we move towards complexity, we are going to put much more of these processes like hydrology or others into the forecast model. And some of them, they don't follow the Navier-Stokes equations. They have to be empirical and they have to be stochastic. So that's a reflection that this is something, is a path to, of line of working. But these stochastic models will also extrapolate the empirical, the observational information into the past and into the future, both the information and the uncertainty. So which processes can be represented? So it's physical parameterization. That's a model, empirical model. What we need is to have the stochastic component in all the physical parameterizations and parameters. We also need, is the question of inaccurate numerics. We have a lot of errors in the interpolation, especially over land, or in the dynamics, for instance. We could have missing processes like chemistry, empirical. So we have an empirical model of stratospheric ozone, but it's not stochastic. It should be so easy to add some stochastic terms constrained by observations. And there are always the unknown sources of model error. And this is a little bit more controversial. And these unknown sources could be either random uncertainty, like SPPT, and there we have to constrain the spatial and temporal scales, or the systematic error, or the bias that I talked about. But in general, that this would be, I think, a framework that would allow reconciliation between different camps, on modeling camps. So I would like to end. Thank you for your attention. With a summary that I leave it for you to read, and then I take questions, if any. Thank you for your attention.
Excellent. Thank you so much for your talk. We can take questions either in the chat, or people can feel free to go ahead and raise their hands, and I'll call on you. So Judith, go ahead.
Thank you so much for your talk, Magdalena. Really, so many things, and so many things you say are so deeply thought through. So I really appreciate it. My question is an S2S application, and this is that I really believe that we need data assimilation, and that data assimilation is the purest source to estimate model error, given all the uncertainties. But when we initialize CSM really nastily by nudging different component models and then putting them together, after 3 weeks, we have very similar skill to ESMWF. We're not quite as good, but almost. And obviously, this is a tricky thing because we're close to zero skill. So we are as good in saying there is very little S2S predictability. But I have really started to wonder if we need data assimilation for S2S applications. And I'm thinking about the atmosphere right now, sort of applications for agriculture and water management. And it was interesting what you showed, this slide about the uncoupled ones, and then they were put together and it led to a big shock. I was wondering if you either know of a study or have an opinion about anomaly initializations versus data assimilation initializations on the S2S timescale. Thank you.
Thank you, Judith. I know that there are studies. I wouldn't have them on the top of my head, and I'm not so sure I would recommend them because blankly, because everything has to be put into context. And my thoughts on your question is that not everybody can or should do data assimilation and reanalysis. That would be very expensive. But there is this intermediate step that is the initialization between. Imagine that you have a reanalysis produced by NCEP, NCARI, CMWF with some models, and then you want to initialize other models with those reanalyses. And as you said, you use nudging, and I think that's the way. And there could be many degrees of sophistication in the nudging, and also in the interpolation for land. So my thinking is that we need to pay much more attention to this initialization step to avoid initialization shock. So either spectral nudging or choosing which variables you are going to nudge and which time scales you are going to nudge. And that may have an impact.
Thanks.
Steve, go ahead.
Yeah, hi, Magdalena. I was wondering if you could say a bit more about using ocean bias correction in forecast mode, because you did make the point that ocean bias is non-stationary. So how do you deal with that non-stationarity?
Yeah, I mean, the bias doesn't need to be applied all the way into the forecast. You have a bias and you have an uncertainty and an error, and it has a time scale. So maybe it's easier if I manage to go to the equation. This is a very simple model of model error, and I wouldn't recommend it necessary. I prefer to think that this coupling empirical with dynamical models is better known targeting processes that you don't have rather than application of bias. In the case of the reanalysis, it's easier because you always have the observations. But did you see in this little model of model bias, we have a term that is constant and an online term that decays. So with some stochastic noise. This stochastic noise can be, that's probably the one that is going to create the model bias. While in this autoregressive model, in data simulation, this stochastic term is constrained by observations. But this is a decay. This is a decay because this alpha is always less than 1. So there is a lot of things to play with. And one of the problems of these empirical models is the amount of tuning is infinite. And then one gets tired. but it could be possible to estimate these parameters, I think, and play with them. So the non-stationarity is taken by this alpha term.
Great. There's a question in the chat. To what extent can a realistic initial state not project onto the model attractor?
To which extent? Well, it's quite a general question, but for instance, I'm going to show one example that we have with the ocean data simulation with equatorial currents. So at the equator, the dynamical balance is quite complex, and density doesn't determine, and there is no geostrophy, or geostrophy is weakened there. So with density, you cannot constrain the current so easily via geostrophy. So you need to put additional balance constraints. If you try to put some slope in the thermocline that the model cannot sustain, you are going to create spurious currents, and that can create imbalances and initialization shock. We see it quite often in ocean and atmospheric data simulation in the stratosphere as well. Does it help? There is also other faster processes that they may have to radiation clouds, how depending on what convective parameterization you have, you may not be able to sustain the humidity that the ocean, the atmospheric reanalysis have. Would that make sense?
We got a thank you in the chat, so I think so. And I had a question about the way that you initialize the spread, particularly in the deep ocean, using the drift of individual models. I guess when you're simulating, especially the infrequent observations that we have in the deep ocean, with maybe a large spread there, I guess what are the implications for sort of setting off, transients in the deep ocean that could, take a very long time to resolve and lead to more drift?
Yes, no, that's another pathological case. We just pray that this is not the case. Well, and then look that it has not been the case, but it happens. And we had problems, we have problems actually in the Mediterranean outflow into the Atlantic at about 2,000 meters. We could have problems there. Yeah. I mean, the ultimate solution is to improve the models. It's only that we have to do something in the meantime, but model improvement is the best, slow, but best way.
All right, well, on that hopeful note, not seeing any other questions. Thank you once again, Magdalena, and looking forward to seeing everyone at this time next week. Take care.
Okay, bye-bye. Thank you. Cheers.